Okay, let's get started with chapter 4. I'll give you guys about a 30-minute to 45-minute video on the intro to 4.1 and some problems in 4.1. So basically 4.1 is starting the chapter where we're going to use applications of derivatives. In your pre-calculus classes, you would talk about absolute mins, absolute maxes, local mins, local maxes, but normally you would just do it graphically. So now we're going to kind of go further than that. We're going to see what derivatives can do for us and all the information they can tell us about a graph. And this is also stuff you'll end up using in Calc 2 and in further math classes. So this is just like I would normally write on the board. I would normally write up 4.1 and I'd give you guys some information and ask you to copy it down. So I suggest you do the same. So take a minute to write all this down. If you need to pause the video to keep up, go ahead. But I'm going to explain each one of these kind of piece by piece. The first thing I'm going to talk about is there are two types of maximum and minimum values, the local or relative max and min, and the absolute max and min. Let me fix this real quick. That's pretty ugly. Much better, but so we have local or relative max and min and absolute max and min. So in general, what I've discovered is that normally it is more difficult to find local mins and maxes or local max and mins than it is to find absolute max and mins. It always seems a little bit easier for me just because of the way that you can calculate the absolute mins and maxes that I'm going to show you today. In both cases, there's normally going to be something you have to do, and it's called finding the critical numbers. So we're going to work with finding critical numbers in this section. That'll be something that we practice. And I need you guys to understand, depending on the book you're using, some books will call it the relative minimum and some books will call it the local minimum or the local maximum or the relative maximum. But they're basically the same thing, okay? An absolute max or min is the highest or lowest, depending on what you're working with, value that the entire function takes on. An absolute max occurs at a point C, and this is the formal way to discuss it, at a point C, if f of c is greater than or equal to f of x for all x an element of the domain of f of x. An absolute min occurs at a point c if f of c is less than or equal to f of x for all x an element of the domain of f of x. So basically what this is saying is if there's some c that you plug into the function f, and it will always be bigger than or equal to any other x you could plug into f in the domain, then you call that a absolute max. It is the highest point on the graph, okay, of your function. Same thing with the min, but just from the other angle. If you plug a c in and it's lower than any x value or equal to the lowest x value that you could ever plug in, or I should say the f of x value you could ever get as a result, then you would say that it is the absolute minimum value, okay? So absolute min, absolute max mean it's the highest or it's the lowest on the entire graph in your domain. We often refer to the absolute max and min as extreme values or extrema of f of x. So sometimes in your book or in the notes, I'll call them extrema. A lot of times they'll say absolute extrema. I have seen some books call it local extrema or relative extrema. I'm not sure if this book does or not, but in general, when you're thinking of extrema, you're normally talking about min and maxes and oftentimes absolute mins and maxes. A local max or min occurs at a point C if f of c is greater than or equal to f of x, or f of c is less than or equal to f of x for some x value near c. Now this is the big thing right here. Near c, okay, x values near c. So they're saying don't, you can't really be ridiculous and talk about a value that's not even close to it. So it's in the neighborhood. A lot of times I use the idea of a neighborhood to describe my local mins or local maxes or relative min or relative maxes, okay? So in general, you kind of have to think of it that way, okay? As near this value of C, all right? So a few key things I want to talk to you guys about. So hopefully you guys had a chance to write all that down. A few key points. And then we're going to look at a picture. So a few key points. Okay. So number one, an absolute max or min may occur multiple times. Absolute just think of like the sine function. You know, what's the maximum height the sine function will ever reach, the basic sine x? Well, the maximum height that it'll ever reach is 1, right? Because we know that the range of sine of a basic sine function is 1, -1 to 1. So we know that the highest point this graph will ever make it to is +1. Does it do that often? Well, yeah, because the sine function goes on forever in both directions. So it's going to repeatedly hit a height of 1, but there'll never be anything higher than 1. So that would be our absolute maximum. And then the absolute minimum, likewise, would be -1. So this can happen. It can repeat itself, okay? A second note or key point is for a point C to be an absolute max, or a local max / min, it must be defined. Okay, so for a point C to be an absolute max min or a local max or min, it must be defined, meaning that it has to be part of the graph. When you plug in the value, it must exist. You can't get undefined, okay? So if you're going to talk about C as a local min or a max, that means you're automatically saying that C is defined on the graph. You can't just say, well, it's the smallest value, but it's not defined there. That doesn't work, okay? Part 3 says, or a third point, for our class, we're going to say if we are looking at a function defined on the interval a to b, then the endpoints x equals a and x equals b cannot, this is important, cannot be local maxes or mins. Okay, so it's very important. I don't know how that drew so perfect. It's very important you understand that we do not in our class allow endpoints to be local mins or maxes. It's just, for me, the way I think of it is, let's say you're in a neighborhood, but you're the last house on a cliff. And you're the lowest, or let's say you're the highest house in the entire neighborhood, but you're on a cliff. There's nothing to the other side of you. Well, you don't really have a neighborhood around you. You're kind of your own little world. So we don't really think of it. We don't really think of you as a local max or a min. You may still be an absolute max or a min, but you can't be a local if you're the last one, if you're the endpoint. So in general, for our class, we're going to say that endpoints cannot be locals or relative mins or relative maxes, okay? Last thing, oops, absolute max / mins are also local max / mins as long as they are not endpoints. So if you find an absolute max or an absolute min, you can also call that absolute max or absolute min a local max or a local min, but it can't be an endpoint because we just discussed above, we're not going to let locals be endpoints, okay? So let me take this minute to draw a drawing real quick. So I'm going to take and just draw this right here, and we're just going to kind of look at this, and I'm just going to draw some weirdness here, some weird function. Ooh, what the? Okay. My graph is not. I do not know why that happened. Okay. So we're going to do this. We're going to do this. Let's do a little of this. Let's do a little of this. Oops. Maybe a little too high. Okay. So let's call this A. Let's call this B. Oops. Oh no. Okay, so let's do this guy right here. Let's call that A. Let's do this guy right here. Let's call that B. Let's call this guy right here C. Let's do this one up here as D. Let's do this one here as E. Let's do this one as G. And let's do this one as H. Okay. So each of these points, A, B, C, D, E, F, H. Okay. I want to discuss what are all of these. Identify each of these points as a local max or a min, an absolute max or a min, both or nothing. So let's put right here, ID local / absolute / both / nothing. Okay, so let's see what each one is. All right. So for A, so we're looking at A, that's right there, right? So A says that's an endpoint, okay? And I think I drew this a little bit bad. Let me draw this a little bit better. So let me just draw it like that. You guys get what I mean. It goes right to there, okay? So that's A, right? If you had to draw a dotted line, it goes down to here. So there's A, okay? So we're looking at A. Now, is A an endpoint? Yes, A is an endpoint, right? So A cannot be a local. So we already know A cannot be a local, okay? Okay, sorry about that, you guys. My computer froze. Okay, so we're back. Okay, so A cannot be in local, but it could be an absolute. Now, is it the highest or the lowest point on the entire graph? No, so I'm going to say that it's actually nothing. I'm going to say that this is actually nothing. Okay, now let's look at B. Now, is he the lowest point of the entire graph or the highest point right here at B? So that was A, we're right here at B. Nope, he's not the highest or the lowest, so B is not a local, I'm sorry, it's not an absolute min or a max. However, in that neighborhood, is it the lowest point in the neighborhood or equal to the lowest point in the neighborhood? Yeah, so I'm going to call this a local min. Okay. Now C, in that neighborhood right here, is he the lowest point or tied for the lowest point or equal to the lowest point? Yep, so I'm going to call him a local min as well. Now up here, when we're looking up there at D, is that the highest point on the entire graph? Yeah, that is the highest point. So I'm going to call that the absolute max. Okay. However, is it also in the neighborhood around here, in this neighborhood near D? Is D the highest point in that neighborhood as well? Yes, it is. So we know that D is also a local max. So it's both, right? It's an absolute max and a local max, okay? Now let's look at E. I'm gonna say right now, it's nothing. And instantly I know it's nothing because that open circle means it's undefined. And we said that a local min or a local max or an absolute min or an absolute max must be defined, right? That was up here. So it says for a point C to be a local min or max, it must be defined. So we already stated that and it's not defined right here. So we know that's not gonna work, okay? So let's look at, ooh, I didn't do F. So let's call this F and G. I messed up on that, E, F, G. Okay, so now what is F? Well, let's look right here. In that area right there, that is the local max, but it is not the absolute max because we already had the absolute max up there. That's the highest point, so it's just a local. Now we go down to here, we're looking at this location. That is the lowest point on the entire graph, so this is an absolute. Okay. Now, why is it not a local min? Well, because once again, it's an endpoint, and endpoints can't be locals in our class. Okay. So that's kind of graphically what we're looking at. So I just kind of wanted to show you guys something. Right here, in this location, right here, in this location, right here, there is something that we've been doing for quite a while. We've been doing tangent lines. So if I wanted to draw tangent lines at those locations, what would their value be? Okay, what would the slope of those tangent lines be? The slope of those tangent lines would end up being 0. So that's going to lead us to another idea that we're going to be working with. So we're going to be working with this other idea that says, well, let me just put it this way. When you see this graph, is it pretty easy to see where there's local mins, absolute mins, local maxes, absolute maxes? So it's pretty easy to identify them, but it gets a little bit harder if I just give you something like this. If I say, how can I say this? Well, we're going to talk about critical numbers. So if I want to find the critical numbers, let's do this. So we notice that the derivative can be 0 or the derivative cannot exist, okay? So I want to show you guys something with this other problem. So if I gave you f of x equals x plus 5 squared times the cube root of x minus 4, okay? So in order to find critical numbers, in order to work with critical numbers, hold on, you guys, real quick. I'm trying to do 2 things at once, and my brain is not keeping up. So basically, visually, it's easy to find critical numbers if you have the graph, okay? We want to know how to find them using calculus, however. So what can we say at the about the derivatives of the points where we had maxes and mins? So if we go up here, we could see that right here, let me just kind of highlight all these locations. So we had a local max at F, we had at E, we didn't have anything. Here at D, we had an absolute min, but we also had a local max. Here we had a local min, and here we had a local min. So at all of these locations, we know that the derivatives did something special. So if I tried to draw a tangent line right here, my derivative, my slope of my tangent line would be 0. If I tried to draw one here, the slope of my tangent line would be 0. Now this one would be kind of hard to talk about because it looks like the derivative is kind of going like this, right here. But then if you come from the other side, it looks like the derivative kind of is approaching a different value. So that might be a situation where we have to run into a derivative that does not exist. Okay, so we have a couple of scenarios that cause local mins or maxes. It's when the derivative does not exist at that location, or when the derivative is equal to 0. So when these two things happen, these are called critical numbers. So let me, So let me write over here. Okay, so a critical number. So a critical number is a number C in the domain, this is very important, in the domain of f of x such that either f prime of c equals 0 or f prime of c equals d and e. Okay? So these critical numbers have to be in the domain of the problem of the original function f of x. So they have to be in the domain of f of x, okay? And whenever f prime of c equals 0, or when f prime of c is d and e, that's when you have a critical number as long as it's in the domain. And we're going to use these critical numbers to help us find local mins and maxes. So first, let's practice finding a critical number. So I'm giving you f of x equals x plus 5 squared times the cube root of x minus 4. Okay, so over here on the side, we have this f of x function, and I want to find the critical numbers. So in order to find critical numbers, you notice that it said the derivative and the derivative. So we're talking about the slopes of the tangent lines. We're talking about the instantaneous rate of change equaling 0 or does not exist. So what we're going to do in general is we're going to first find the derivative of our function. So that's why you needed chapter 3, so you could get better at finding derivatives. So we have f prime of x is equal to, let me rewrite this first. Let's do a little rewrite over here. This is going to be x plus 5 squared times x minus 4 to the 1/3 power. Okay. So that means when I take the derivative of this, this is going to be 2 times x plus 5, rewrite x minus 4 to the 1/3 power, plus x plus 5 squared times 1/3 x minus 4 to the negative 2/3 power. Okay, so all I did was I took and I did the product rule. Okay, so it's not like we can forget that. So here's the thing. Many of you, now you have to find out when this function, or I'm sorry, when this derivative would equal 0. So you might make a guess and you might say, well, when x equals negative 5, this guy would become 0. And what's 0 times all that? 0. This guy would become, when x equals negative 5, this guy would become 0. So all of this would become 0 as well. So you might say that, okay, so that's a good situation. So I'm pretty sure I guess that one of my critical numbers is probably, I'm going to say probably x equals negative 5. Could you guess another one? Well, I'm pretty sure if I want to break this problem, if I want this problem to be undefined and break the derivative, I'm pretty sure that if I say x equals 4 and I plug that in there, wouldn't I get 0? Okay, well that sounds fine, but when I put it in here, this is a negative exponent, so that's going to actually be in the denominator. So now I have a situation where I'm trying to divide by 0, which is undefined, so our derivative in this situation does not exist. So I'm pretty sure that 4 is also going to be 1, but now the problem is technically, did we do our calculus right? Technically, our calculus is done. But in the previous sections, I used to make you guys factor and simplify your work and do all of that stuff, or make common denominators. So we're going to have to do that again. So what I'm going to do is I'm going to rewrite f prime of x in a cleaner form, because as it turns out, there's actually a third critical number, but there's no way you could guess it just by looking at it. So what I'm going to do is I'm going to clean up this function, and I'm going to say this is 2 times x plus 5 times x minus 4 to the 1/3 power, plus, and then I'm going to put the negative exponent in the denominator. So this will become, you know what, let me leave a little space right here, plus x plus 5 quantity squared divided by 3 times x minus 4 to the 2/3 power. So I used up the negative exponent and I put it in the denominator. Now you guys all know that if I want to make these be common denominators, this is really 2 over 1. So I look over here and I say, what does this guy have that this guy needs right here? He needs a 3 times an x minus 4 to the 2/3 power. So now I would technically have the same denominators. However, whatever you do to the denominator, whatever you do to the denominator, you have to do to the numerator. So let me rewrite this a little bit better so we have more room. So this is going to be plus, and then I'm going to do x plus 5 squared over 3 times x minus 4 to the 2/3 power. So then I'm going to do 3 times x minus 4 to the 2/3 power over 1. So now notice that I did 3 times x minus 4 to the 2/3 power to the numerator and the denominator, okay? So that means I now have common denominators and I have not changed the worth of the problem. So this now will become 2 times x plus 5. Now when you take, that's actually 6, right? Because I got to do this 2 and this 3, I got to multiply them. So this is actually 6 times x plus 5 times x minus 4 to the 1/3 plus 2/3. Because they're both same bases, I can add powers. So this becomes to the 3/3. So this becomes 1 plus x plus 5 quantity squared all over 3 times x minus 4 to the 2/3 power. Okay, everybody okay with this so far? So hopefully this is making sense. Now the thing is instead of foiling all this out, which you could do and it would work, a lot of times it's easier to just factor this out. So we're just going to say f prime of x is equal, let me see here. Well, I can factor out the x plus 5. You know, I'll put brackets around it. I'm going to factor out the x plus 5. And again, I'm getting that because here's an x plus 5 and here's an x plus 5 and there's a plus sign. So I have to factor it from both of them. And then what's that going to leave behind? Well, that's going to leave behind a 6 times x minus 4 plus an x plus 5. Okay, so let's clean this up all over. 3 times 4 to the 2/3 power. So f of x is equal to x plus 5. I probably should have put brackets around this other part, but that's okay. So this will now be 6x plus x, so that's going to be 7x. And that'll be minus 24. Distribute that. And that'll be minus 24 plus 5. So it'll be minus 19 all over 3 times x minus 4 to the 2/3 power. Okay, so remember, let's go back to here. We said x minus 4 and, or I'm sorry, x equals negative 5 and x equals 4 were probably critical numbers, and we're right. If I set the denominator factors, so I'm going to come up here. If I set the denominator factors equal, we have x minus 4 to the 2/3. Well, you know what? You don't even have to do to the 2/3. You can just do x minus 4 because whether it's 0 to the 2/3 or just 0, it doesn't matter. We're going to set that equal to 0. That's our denominator. So we're going to take the denominator and put them here. Then we're going to take the x plus 5 factor from the numerator and set that equal to 0. And then we're going to take the 7x minus 19 factor and set that equal to 0. So you guys hopefully see what I'm doing here is I'm taking each factor and setting them equal to 0 because we want to find out when the derivative is 0 or undefined or does not exist. So we come over here and we have x equals 4. Over here we have x equals negative 5, and over here we have x equals 19 over 7. So these are in fact my 4 critical numbers. Now, something I have to double check real quick is it says critical numbers, a critical number is a number C in the domain of f of x. So you always have to double check the domain of the original function. So we go back to f of x, not f prime, but we go back to f of x. What is the domain of f of x? The domain of f of x is all real numbers because number one, this is a polynomial times a cube root. Cube roots have negative infinity to positive infinity. They don't have any issues, and polynomials don't have any issues. So these have no domain issues, okay? So we don't have to worry about domain. The domain is negative infinity to positive infinity. So we actually have 3 critical numbers. And I think you guys can guess there is no way you would have found 19 over 7 without going through and doing the work, okay? So that's one problem. And as you can see, these aren't easy. These take a little bit of time, okay? So let's take a look at something else. So I'd like you guys to take a minute to try this one. Suppose we have h of t is equal to t to the 3/4 minus 2t to the 1/4. Okay, so t to the 3/4 minus 2t to the 1/4. So pause the video, and I'd like you guys to see if you could find the critical numbers for this. Okay, so find the critical numbers. Okay, pause the video and give it a shot. Okay, so hopefully you guys have unpaused the video instead of just listening straight through, otherwise it'll sound funny. Let's find h prime. And remember, to find a critical number, we have to find out when the derivative is 0 or undefined. So I'm going to find this derivative. This would be 3/4 t to the what? Negative 1/4, right? Minus 2 times 1/4 t to the negative 3/4. This is just our general power rule. No big deal. We're just kind of going through this. Now let's make them have positive exponents so we can see what we're dealing with. Do a little cleanup real quick. So this will be 1 over 2. You know what? I probably shouldn't have done that because they were already common denominators. Let me go back and fix that. Normally, I would say clean everything up you can, but they both have a 4 for a denominator right now. So I'm just going to leave that because I'm going to end up having to put it back together anyway. So we have 2 over 4t to the 3/4. So now they both have 4s. The denominators both have 4s, but now we need to see what would make them be identical. Okay, so where could we make them meet at 1/4, or do we make them meet at t to the 3/4? So I can take a 1/2 power and I can turn it into a 3/4 power. Okay, or think of it as, how can you make a 1/2 become a 3/4? Well, if you add a 1/2 to a 1/4, you would get 1/2 plus, 2/4 plus a 1/4 is 3/4. So in order for these to be common denominators, I need to multiply this by t to the 1/2 times t to the 1/2, okay? And when you have same bases, like these are, remember, all you do is add their powers. So this is now going to become h prime of t. Oops, sorry, I already wrote that. So this will become 3t to the 1/2 minus 2 all over 4t to the 3/4. So 3t to the 1/2 minus 2 over 4t to the 3/4. Okay. Now we come over here and let's see here. We're going to take the numerator, 3t to the 1/2 minus 2. And we're going to set it equal to 0. And then we're going to take the denominator. I don't need the 4. I'm just going to take the t to the 3/4. Set that equal to 0. Because if you put the 4, when you divide by 4, it would eat it up anyway. So that means that here t equals 0. And over here we have 3t to the 1/2 equals 2. 2 over. And then we divide both sides by 3. So we now have t to the 1/2 is equal to 2/3. But then we have to square both sides to get rid of the 1/2 power. So we get t is equal to 4 over 9. Now, I feel like these are my critical numbers. But what should I double check? I need to double check the domain. So am I allowed to plug both of these numbers back into the original problem without causing domain issues? Well, if I take 0 and I plug it in here and I plug it in here, I get 0, which is fine. That's an okay answer. And if I take 4/9 and I plug it in here, I plug 4/9 back into here, or I plug 4/9 into here, I get some fractions, some ugly decimals, but either way, it's not imaginary, it's not an issue, so it's okay. So both of these are in the domain, so these are both critical numbers, okay? So we are gonna take these as our critical numbers, we'll take them, okay? Any questions about that? You guys be sure to ask me when we meet, okay? Let's see here, let's move on. So now we know how to find critical numbers. Now let's talk about how we can use them. Oops. So let's talk about the extreme value theorem. So this is the extreme value theorem, okay? The extreme value theorem. So the extreme value theorem says if f of x is continuous on a closed interval a to b, very important, closed interval part, closed interval a to b, then f of x attains absolute max f of c and absolute min f of d for some c and d element. Okay. So here's the thing. The extreme value theorem is basically our way that we're gonna use this concept to find absolute mins and absolute maxes. Okay. So what the extreme value theorem does is it's a promise. It's a money back guarantee, and it says if f of x is continuous on a closed interval, so they're telling you these two things have to be true, that the function must be continuous and the function must be, the interval that you're dealing with has to be closed, right? So you have endpoints is what it's basically saying. Then the extreme value theorem promises you that if f of x attains an absolute max f of c, and then it does attain an absolute max f of c and an absolute min f of d for some c and d and element of a and b. What it's saying is that if you have a closed interval and it's continuous, that you're going to get an absolute min and you're going to get an absolute max. Okay. The key is the interval has to be closed and it has to be continuous. Okay. Think of all the weird scenarios where if it wasn't a continuous function, you could teleport, you could do all kinds of stuff, and you know your graph could just jump around. So they're saying these two criteria have to be met. Okay. So what we're going to do is we're now going to use the extreme value theorem to come up with a way to find absolute mins and maxes. Okay, finding absolute slash maxes, or maxes slash mins. Let's do that. I've been writing it max min the whole time. Okay. So first thing we have to do is make sure your function is continuous on a closed interval. So make sure you have continuity on a closed interval. Okay, and in general, that oftentimes seems like an afterthought. Part two, I shouldn't say an afterthought, but for a lot of the problems, it's gonna be, because I'm trying to get you to answer certain questions. Find the critical numbers, very important. 3, evaluate your function f of x at your critical numbers and endpoints. Okay, because remember, endpoints can be absolute mins and maxes as well. They don't have to have their derivative equal to 0 or undefined at those locations. They just have to be the highest or lowest point on the graph. And the fourth thing is the largest value is your absolute max. Smallest value absolute. Okay. So that's a lot of talking. Let's actually try one of these. Okay. So let's go down here a little bit. What we got. Okay. So it says find absolute slash max. Okay. So we have f of x equals x cubed minus 12x on 0, 5. Now, the important thing is x cubed minus 12x, you know right away that's a polynomial. And what do we know about all polynomials? They're continuous. So boom, we're done with that. Next thing we see is they gave us an interval from 0 to 5. So that's our domain, that's our interval, and it's closed. So what did the extreme value theorem promise us? The extreme value theorem promised us that if we have a continuous function on a closed interval, we are guaranteed to find an absolute min and max. So all I have to do is find f prime. That would be 3x squared minus 12, okay? And now I have to find my critical numbers. So I'm going to set this equal to 0. So this would be 3 times x squared minus 4. I'm going to take x squared minus 4 and set it equal to 0, all right? Just taking this and putting it right there, okay? And then we have x is equal to plus or minus 2, okay? Or you could say x equals 2, x equals negative 2, all right? So these are what I think are my critical numbers, but there's a problem, okay? What's my interval? From 0 to 5. So as it turns out, I cannot use the negative 2. So this is my only critical number, okay? So now we look at rule 3, or not rule 3, but step 3. It says evaluate your function at your critical numbers and your endpoints. So right here, I'm going to do some evaluating. So right here, I have f of 0, f of 2, and f of 5. So as you notice, these two guys are my endpoints, and this guy is my critical number. Oops. This guy is my critical number. So I'm evaluating my critical number and my two endpoints. And all I'm looking for is the biggest number and the smallest number that I get for my outcome. So when I plug 0 into my original function, I get 0 cubed minus 12 times 0 equals 0, right? When I plug 2 in, I get 8 minus, what, 24? I get 8 minus 24, so that would be, what, negative 16. And when I plug 5 in, I get 125 minus 12 times 5. So I believe that's 60, 125, so that would be 65, I believe. So we have that. So which is the biggest number? This guy right here is the largest number. So we're going to say that 5, 65 is my absolute max. What's the smallest number? Negative 16, right? Negative 16 is my smallest number. So we're going to say 2, negative 16 is my absolute. We're done. That's it. That's how we can use the idea behind, or the money back guarantee behind the extreme value theorem to help us find our absolute min and our absolute max. So it's pretty straightforward. The confusing part becomes when you learn the first derivative test. Sometimes you'll be plugging into derivatives, sometimes you won't be. So that's when it gets a little bit confusing. Okay, so let me see. I think we can do one more. Let me give you guys a little bit harder one. Oh, that one's too hard. Let's wait on that one. Let's do this one. Let's do one more. Let's say that we have f of x. Let's call this example number 2. F of x equals minus 1 to the 2/3 power plus 2 on the closed interval 0 to 9. So let's find our absolute mins and our absolute maxes. So first thing we have to do is f prime of x is equal to 2/3 x minus 1 to the negative 1/3 plus 0. We're going to rewrite this. So we're going to have f prime of x is equal to 2 over 3 times x minus 1 to the 1/3 power. I used up the negative exponent. And then once again, I'm just going to take this guy over here. X minus 1 is equal to 0. And again, you guys, a lot of times I leave off the powers and stuff because when something becomes 0, the power won't matter, right? So I'm just going to find out when would x minus 1 be 0. Well, that would be when x equals 1. Now, is 1 in our interval? Is 1 in here? Yes, it is. So then we get to count this. This is a critical number. Okay, and we have 2 endpoints. So all we're going to do is we're going to do f of 0, f of 1, and f of 9. Should be pretty straightforward. When you plug 0 in, you get negative 1 squared would be 1, cubed would be 1, plus 2 would be 3. We get 3 right there. When I plug 1 in, I get 0, plus 2 would be 2. And then when I plug in 9, I get 8, cube rooted would be 2, squared would be 4, plus 2 would be 6. Oops, you know what, since I didn't skip all those, this is 6, I believe. Okay, so now once again, all I do is I look and I say, well, right here, this is my largest value, so I know that 9, 6 is my absolute highest point. This is my absolute max. Then over here, oops, wrong one. Oh no, that's the right one. This is my lowest point, so 1, 2 is my absolute minimum value. Okay, so this is kind of a good way to get started on the homework. Obviously, you're going to have some stuff with sines and cosines. I'll maybe do one of those in a video tomorrow. And we'll do some stuff with sines and cosines and e to the x's and natural logs and all that. I will say that natural logs are normally a little bit harder to work with, but in general, this is how we do it. This would be the answer that I would expect to see on an exam. Okay, and I need to see your work. You can't just look at a picture and say, oh, that's the highest point. All right. All right, guys, that video went a little bit longer than I wanted, so I'm going to just save this one and we'll go from there. Sorry about the computer crashing in the middle of the video. Okay. See you guys tomorrow.